What if I tell you that everything you learned about atoms in school is wrong? Not slightly, not technically, it's completely impossible. And if it were true, you wouldn't exist. The chair you're sitting on wouldn't exist. The air you're breathing wouldn't exist. Because according to the laws of physics, every atom in the universe should destroy itself. So why doesn't it? To answer that question, we need to uncover one of the strangest secrets in science: what atoms actually look like. This image is everywhere. It's in textbooks, on classroom walls, in science museums, and maybe even in your head right now. A tiny nucleus sits at the center, while electrons circle around it like planets orbiting the sun. Simple, elegant, easy to understand. There's just one problem. Nature hates it. An object moving in a circle is constantly changing direction. And changing direction means accelerating. According to electromagnetism, any accelerating electric charge radiates energy away. Electrons are charged, so orbiting electrons should continuously lose energy. Like a race car burning through fuel, the orbit should shrink faster and faster and faster until the electron crashes into the nucleus. Not after millions of years, not after seconds, almost instantly. If atoms really looked like tiny solar systems, every atom in the universe would collapse, matter wouldn't exist, you wouldn't exist. Yet here we are, which means somewhere in this picture we've made a terrible mistake. In 1924, a young French physicist named Louis de Broglie proposed an idea so bizarre that it sounded absurd. Maybe electrons aren't just particles, maybe they're waves too. Not just light waves, not just sound waves, matter itself. Everything in the universe has a wave nature. For baseballs, cars, and people, those waves are so tiny that we never notice them. But electrons are different. For electrons, the wave isn't a tiny correction, it is the whole story. And once you accept that, the atom becomes much stranger, because waves don't live in one exact place. They spread out, they occupy many possibilities at once, which leads us directly to one of the most famous ideas in all of physics, the uncertainty principle. Nature refuses to reveal an electron's exact position and exact motion at the same time. The more precisely you know one, the less precisely you can know the other. The electron stops being a tiny planet and becomes something else entirely, a cloud of possibilities, cloud of probability. Imagine you're trying to find where a child spends their afternoons. Every day, at exactly 2 o'clock, you take a photograph, day after day, week after week. At first, the positions seem random, but eventually, a pattern begins to emerge. Maybe they're usually at the park, sometimes at the playground, occasionally near the corner store, rarely near the busy road. The map doesn't tell you where the child is right now, it tells you where you're most likely to find them. That's exactly what an orbital is. Not a path, not an orbit, not a track that an electron follows. An orbital is a three-dimensional probability map, a forecast of where the electron is most likely to appear. But this creates a new mystery. Why do orbitals have such strange shapes? Why spheres? Why dumbbells? Why giant cloverleafs floating in empty space? To answer that, we need music. Imagine a guitar string. When you pluck it, waves travel along its length. But because both ends are fixed, not every vibration survives. Only special patterns can exist. These patterns are called standing waves. Some parts of the string move dramatically, other parts never move at all. Those motionless points are called nodes. Now imagine a drumhead. The nodes become lines. And when we move into the three-dimensional world of atoms, those nodes become entire surfaces cutting through space. Regions where the probability of finding an electron is exactly 0. And here's the incredible part. Electrons are waves trapped around a nucleus, which means electrons form standing waves too. The atom isn't a miniature solar system, it's more like a tiny musical instrument, and orbitals are the notes it can play. The simplest standing wave creates the simplest orbital, the s-orbital, a beautifully symmetrical sphere surrounding the nucleus. No complicated geometry, no strange twists, just nature's lowest energy solution. But add a little more energy, things become weird. A node appears, an invisible plane slicing through the center, a region the electron can never occupy. The spherical cloud pinches apart, creating two separate lobes, the famous p-orbital, the shape that looks like a dumbbell floating in space. And because space has 3 dimensions, there are exactly 3 ways to orient it: along the x-axis, the y-axis, or the z-axis. 3 p-orbitals, no more, no less. Add even more energy, and more nodes appear. The wave becomes increasingly complex. The atom starts growing flowers, 4 lobes, loops, donuts, cloverleafs, shapes so strange they look like sculptures designed by an alien civilization. But they aren't artistic inventions. They're the natural consequence of standing waves existing in 3 dimensions, the geometry of quantum mechanics, made visible. And now for one final surprise. You might think the letters S, P, D, and F describe the shapes of the orbitals. Maybe S stands for spherical, maybe P stands for peanut, maybe D stands for dumbbell. Nope, not even close. These letters are actually older than quantum mechanics itself. Long before anyone understood atoms, scientists studied glowing spectral lines. They classified them as sharp, principal, diffuse, and fundamental. The names stuck. Even after physics completely reinvented our understanding of reality. So what do atoms actually look like? Not tiny solar systems, not miniature planets orbiting a microscopic sun. Instead, they are standing waves of probability, 3-dimensional quantum harmonies vibrating around a nucleus, the weird spheres, the dumbbells, the cloverleafs, the strange floating donuts. They aren't mathematical tricks, they are the actual architecture of reality. Every chemical bond, every molecule, every living cell, every star, every planet, every person, built from these invisible quantum shapes. The textbook atom is easier to draw, but the real atom, the atom that actually exists, is infinitely more beautiful. Reality isn't made of tiny balls orbiting each other. Reality is made of waves frozen into shape.